Okay, I guess we'll go ahead and get started now. Anybody have any questions on anything? The lecture test was pointed out to me today that it ended very early in the morning, and I fixed that. So it now ends at 11:59 p.m. on the 13th like it was supposed to. I don't know why eLearn did that to me, but anyway, I've pushed it back to its correct time. So if you haven't taken it yet, you've got till almost midnight on the 13th. Okay, today we're going to go ahead and start on the urinary system, and we're looking at the physiology. We've already done all the anatomy on the urinary system, so we're all experts on the urinary system structure. Okay, so I can dream. So anyway, but today we're going to talk about how the kidneys do what they do. How do they filter our blood 60 times a day? So before we get started, are there any questions on anything? Okay, and I'm going to go. Oh, thank you. Yes, goodness. I tell you, it's Monday. Okay. Now we can see it. At least you didn't wait till I was like 10 slides into it. I had that happen. Yes.
You know, I was on pond last week, so I just had to make up for last week.
Okay, we just were getting ready to start on the urinary system. Okay. We know that the kidneys are the filtering units of our blood. We know that the kidneys regulate fluid levels and ion levels, and they filter out waste products. The structural unit that does that for us in the kidneys is the nephron. There are 1 million nephrons in each kidney, and they are where filtration takes place. Now, the nephron takes advantage of those fenestrated capillaries. It uses a structure known as the glomerulus. The glomerulus is a ball of capillaries that are fenestrated, so they're like a sieve, and they filter out anything that can go through those openings. It's like a colander for spaghetti. The water goes through and the spaghetti doesn't, or whatever else you're filtering through the colander. Little things will go through these fenestrations. Anything that'll fit through there will go through. It's indiscriminate. It's all based on size. Little things go through like vitamins and amino acids and sodium and potassium and calcium and magnesium and glucose. All these things will go through. And water, of course, lots and lots of water. We want to recover most of this. But it will also take out the waste products too, the nitrogenous protein waste and any chemicals and any toxins and stuff like that will also get through. And if it doesn't get through and we want to get rid of it, we can secrete it later on. So anyway, the glomerulus is the filtration unit. The glomerulus is surrounded by a capsule called Bowman's capsule. And so all the stuff that's pushed through the glomerulus is captured by Bowman's capsule, and that whole thing is called the renal corpuscle, and that leads to the first of the kidney tubules, the proximal convoluted tubule. And the whole thing looks like this. This is a nephron. We have the Bowman's capsule surrounding the glomerulus. We have the Bowman's capsule leading to the proximal convoluted tubule. That's a structure here. That leads to the loop of Henle, back up to the distal tubule, and the collecting duct over here. By the time we're down into the collecting duct, we're finally called urine. Up until this point, up here, we're still called filtrate because we can still recover material. Now, this is what this structure looks like. Let me bring it up to the right camera. And it looks, that's what a glomerulus and Bowman's capsule looks like right here. These are all fenestrated capillaries. This is the capsule. This is the beginning of the proximal convoluted tubule. And this structure over here is actually the distal convoluted tubule. The only thing wrong with those diagrams that we see where it's all stretched out flat is that isn't how it looks, because the tubule, the whole nephron is flipped over on itself. So the distal tubule butts up against the afferent and the efferent arterioles. This is where we're going to get, we're going to be monitoring our blood pressure and sodium concentration right in this level here. But this is the glomerulus. This is the Bowman's capsule. This is down here is the proximal tubule. Now back to this. So what we're seeing here in this diagram is actually incorrect as far as how it really fits. This distal tubule section right here is actually folded over so it butts up into this space right here. So anyway, now, and this is a more realistic illustration of it. You can see how there's your distal tubule here. There's your proximal tubule, comes out this way, goes down to the loop of Penley, back up, butts itself up in between the afferent, efferent arteriole right here. And this is what the whole thing looks like. So we have the filtration site, the fenestrated capillaries of the glomerulus right here. There's the proximal tubule. And the filtrate goes down through the proximal tubule where we reabsorb most of our water, most of our salt, all of our glucose, and then it comes back up on the distal tubule, and that's where we secrete substances that we want to get rid of, larger molecules, toxic chemicals that we filtered out of our food supply, for example, or out of our blood. Potassium, we excrete a lot of potassium in the distal tubule. And from there we go into the collecting duct where we can get water one more time. So, okay. Now the nephron is highly vascularized. It has to be, because the kidneys filter our blood 60 times a day. And we filter our entire blood supply 60 times a day. That's a lot. You know, we run about 180 liters of blood through the kidneys. Now we don't have 180 liters of blood. We barely have 6 or 8 liters of blood. So that means we're running it through the kidneys a lot. So it is a highly vascularized region in here. And each one of these little structures right here, these little round things are a glomerulus. And each glomerulus is supplied by an afferent arteriole and drained by an efferent arteriole. And that's really unusual because it's the only place in the body where we have a capillary bed drained by an arteriole. Because normally in capillary beds, we have an arteriole going into the capillaries and we have a venule coming out. But here we have an arteriole going in and an arteriole going out. And the reason we do is that lets us adjust the pressure inside the glomerulus, because the arterioles both have an arteriole has smooth muscle, and it has the ability to respond to norepinephrine by either constricting the smooth muscle or relaxing the smooth muscle. So we have control on each end of the capillary bed. And so we have these arteries here called the arcuate artery, and we have the interlobular artery here. And there's a whole lot of names of the arteries, which we really don't need to spend a lot of time on. in here, but we can say that it is a highly vascularized region. So, and I just said all that. Well, here it's something to point out is the afferent arterioles are going to be larger in diameter than the efferents. And so your pressure is always going to be high, higher in the glomerulus to force things out. Not real high, not like 120 millimeters, more like in the neighborhood of 25 to 40, maybe 60 millimeters at its greatest. But you're going to maintain a high enough pressure in the glomerulus by having blood come in under relatively high pressure. We can adjust the pressure of the blood in the glomerulus by opening or closing the afferent arteriole. And what also helps is that the efferent arteriole is smaller. The arteriole that drains the blood out of the glomerulus is smaller in diameter than what goes in. So we always have more blood going in than we can get out. And in doing so, we have a little bit of a back pressure there that's forcing materials out through the fenestrations. So the three tubules, proximal convoluted tubule, simple cuboidal cells, we always pointed out back in the beginning of AP1 lab, these are the simple cuboidal cells. You find them in the kidney tubules, and then everybody forgets that till AP2, but that's okay. They are, the proximal tubule is made up of simple cuboidal cells. The distal tubule is made up of simple cuboidal cells. They are the site of transport from the tubule into the capillaries that surround the tubules. So we have simple cuboidal cells. The proximal tubule gets about 60 or 70% of the water that has been filtered through here, because we can't lose that water. We can't lose that water. We have to recover it. We have to get all the glucose back. That glucose doesn't belong in our urine. It belongs in our blood. We want to get our vitamins back. We want to get our amino acids back. We don't want to get the nitrogenous waste, the urea and stuff like that back. We want to leave that back in the filtrate. We run the filtrate through the loop of Henle. One side of the loop of Henle allows us to recover water. The other side allows us to recover salt. By the time we get to the end of the loop of Henle, we've probably recovered about 90% of the water. But we have one more chance yet. The distal tubule, it's more about secretion. You want to get rid of chemicals, in food. This, for example, if you like to eat asparagus, most people know what happens when you eat asparagus. It makes your urine smell funny. You're secreting the chemical that does that at the distal tubule. And so if you can smell that, or if it's there, it means that your kidneys are doing a pretty good job in getting rid of that waste product that you don't need. So the same with if you eat a raw onion, you're going to get the same odor, you're going to be able to smell the onion odor in the urine and it's coming from where the chemical that causes that is being secreted at the distal tubule. We secrete potassium at the distal tubule. If you remember the whole action of aldosterone, remember aldosterone? Aldosterone raises blood pressure by retaining sodium and retaining water. Well, to retain sodium, we have to get rid of potassium. We've got to have a balance there. So if we keep sodium, we've got to get rid of potassium. We secrete the potassium at the distal tubule. The distal tubule then leads into the collecting duct. And the collecting duct is the last place we get to try and recover the rest of our water. And the collecting duct is where antidiuretic hormone works. So that's where it acts in the collecting duct to make it either permeable to water if the antidiuretic hormone is present, because after all, antidiuretic means anti-P. So we recover our water the last bit of water we can recover at the collecting duct. And it's enough to change our filtrate from a very dilute urine. If it was released as filtrate, it would be a very dilute urine, or to pull enough water out of it to make it a very concentrated urine. So the role of antidiuretic hormone comes into play here to recover enough water to alter the makeup of our urine, so that what we are peeing out is recovering as much water as possible. Okay, now the nephrons, most of our nephrons are located in the cortex of the kidney. If you remember, the cortex is the outer region of the kidney. If we look at our model here, we look over here at the kidney model, we can see that the cortex is this region along in here. There's the capsule. This is the cortex. This is the medulla. The renal pyramids are always the medulla. And these things are all nephrons. Most of our nephrons are going to be our cortical nephrons. The other type of nephron, the 15% or so, are what we call the juxtamedullary nephrons that run deep down into, like this one that runs deep into the medulla. The loop of Henle is very, very deep in here. Now, why do we do that? Well, most of our purpose of our nephrons is to filter. 85% of the filtration takes place in the cortex. We're going to get back our glucose and a lot of our water and a lot of our sodium and anything else we want to recover, the amino acids and the vitamins. The juxtamedullary nephrons are all about recovering water and sodium. So they give us they can produce a very concentrated urine. Now we don't use, since only 15% of them are involved, if all the nephrons are involved, we're using them to regulate the concentration of our urine. Is it going to be bright yellow or is it going to be transparent? So it just depends. Now to recover all this water, we have several capillary beds. Capillary beds run right beside, the capillaries run right beside the tubules. So you have the peritubular capillaries that surround next to each tubule, and of course you got the glomerulus. The glomerulus counts as the capillary bed. We don't think of it that way. We think of it as a filtering structure, but it really is a capillary bed because it meets the definition. It has blood coming in and blood going out. Where all the recovery, though, comes in are on what we call the peritubular capillaries. These are the capillaries that are adjacent to the proximal tubule, the loop of Henle, and the distal tubule, and the collecting duct. So while each glomerulus is a capillary bed, because it has an arteriole feeding into it, also has an arteriole leading out of it, it's still a capillary bed. Here is the glomerulus up here. But if you take a look at this, you can see that those little purple things are all the, I don't know why they picked purple. All these little purple things here are the peritubular capillaries, and they surround the tubules. Remember, the tubules are only one cell layer thick, and the capillaries are only one cell layer thick. It's easy to move stuff from the capillaries into the filtrate if we want to secrete a waste product. If we want to recover something, it's easy to move it from the filtrate into the capillaries. That's where we recover our water. That's where we recover how we recover our sodium. That's how we recover glucose. If we want to get rid of something, it's very like, the odor causing agent of asparagus, for example, we can secrete it from the capillary into the filtrate. But we see we have these peritubular capillaries surround both the proximal and the distal tubule. And we have what are known as the vasa recta, the capillaries that surround the loop of Henle. Because the loop of Henle is going to be busy recovering about 30% of the water. We get about 60% at the proximal tubule, about 30% in the loop of Henle. We get a lot more salt from the loop of Henle, out of the loop of Henle too. It all has to go back into the plasma. And I just said all that. So the peritubular capillaries and the vasa recta. So now, what makes the glomerulus work so well is that, first of all, the arterioles, the afferent arteriole is larger than the efferent arteriole. And we tend to maintain a pretty constant blood pressure in there, not the full-blown pressure like in the aorta at 120. We're probably around 60. And so we have some pretty good pushback from the arterial walls here. We don't get a lot of bounce around in here. It doesn't matter what the blood pressure is doing at any given time. You run up a flight of stairs, your afferent arteriole is still going to stay around 60. You're sleeping, your blood pressure drops. Your afferent arteriole is going to still be pretty constant because of the resistance in the arteriole, the pushback against the arterial wall. The problem comes in where our own systemic blood pressure starts rising. Because we're talking if the blood pressure is 120/80, we're happy, we're good. That's a nice number. But what if it goes to 200/100? That's going to affect the glomerular pressure too. And so one of the long-term consequences of hypertension is kidney damage, because you're pushing this higher pressure blood into the afferent arteriole. It's going into the glomerulus, and we're dealing with, these are all one cell layer thick structures. It doesn't take much to start damaging, well, I mean, it's not like it's not like one day your blood pressure goes up to 200, the next day your kidneys are shot. It's not like that, but it's over time. Constant elevated blood pressure is going to damage the kidneys. So anyway, the efferent arteriole is sort of the safety valve. The efferent arteriole keeps the pressure, maintains the pressure in the glomerulus because it's a smaller structure. It also prevents high pressure blood from maybe in the glomerulus from entering the peritubular capillaries. So we have this little check in here so that yes, 60 millimeters is coming in, but by the time we get down to the efferent arteriole leading out into the capillaries, we're going to be low enough that the capillaries aren't damaged either, because we don't want that. We want the capillaries to maintain, high enough pressure to move the blood through, low enough pressure that there's no damage. So we can, as we say, we reduce what we call the hydrostatic pressure. The pressure stays low in the capillaries so we can have good exchange across the capillary wall. Remember, it's still only one cell layer thick. We don't want to blow it out, which is what happens when a person has hypertension. Okay. So here's some numbers. 180 liters, that's how much fluid, how much blood and plasma, the whole blood, is run through the kidneys on a daily basis, 180 liters. We only produce 1.5 liters of urine. Because when we get into fluid and electrolytes, you're going to see that the total amount of fluid that we lose on a daily basis is only 2.5 liters. And we recover that on a daily basis too. The kidneys filter our blood 60 times a day. So we're running to get that 180 liters of blood filtered. we're running through our kidneys about every 45 minutes, our entire blood supply. We use a lot of oxygen to do that. About 20% of the body's oxygen is used by the kidneys. So we're filtering it a lot, and all the glomerulus is nothing but a sieve. That's really all it is. It's just a sieve, and things that are small enough to fit through the fenestrations in the capillaries will go through, and things that are too big won't. Large molecules won't get through. And if we want to get rid of those large molecules, we have to actively secrete them. Now our filtrate, we call it filtrate from the moment it leaves the glomerulus and goes into Bowman's capsule, it's filtrate. And it stays being filtrate until it enters the collecting duct and antidiuretic hormone has acted on it or not acted on it. So we don't really call it urine until we're well into the collecting duct. So what is the filtrate? It's essentially everything but the proteins. It's plasma without the proteins, because the proteins are big. We don't, the most common protein in plasma is albumin. It's too big to fit through the openings. We don't see that. We shouldn't see things like red cells show up in our urine or white cells. They're too big. So the filtrate is the salt water with the sodiums and potassiums and hydrogens, bicarbonate ions and things like that can fit through the openings, but nothing big. And then we filter out. We keep pulling back the ions we want, the molecules we want, until we end up with urine. And the urine has all the what we call the nitrogenous waste made from metabolic activity, like the breakdown of proteins, for example, the destruction of old red cells, for example, all of these metabolic wastes that are formed. Anything we want to get rid of, like odors from onion or odors from asparagus, or chemicals from food, or chemicals from medication that we've taken. The amount of urine that we actually produce is less than 1% of our original filtrate. So it is a very, very small amount of what we filtered out ends up here. So to get 1.5 liters out of 180 liters, you can see where we get to less than 1%. So how much plasma is going through here? Well, about 20% of the plasma of the blood, of the plasma that goes into the glomerulus gets filtered every pass. So at any given time, about 20% of our blood is being pushed through our glomeruli. Things that were too big are going to get secreted. Things that are small are going to, I keep saying that, but that's exactly how the kidneys function. We also can we can filter or secrete sodium, potassium, hydrogen, and bicarbonate. So we can regulate our salt concentration or our potassium levels or our pH, because the hydrogen ions, the more hydrogen ions we have, the more acidic we are, the more bicarbonate ions, the more basic we are. So we can the kidneys regulate our chemical makeup of our blood. They can make it more acidic, they can make it more basic by either retaining hydrogens and kicking out bicarbonates, or retaining bicarbonates and kicking out hydrogens. It's one or the other. You don't retain both, you don't kick both out. You kick out one and you kick out the other. Same with sodium and potassium. If you retain sodium, you're kicking out potassium. If you retain potassium, you're going to kick out sodium. We don't keep both. One has to go to stay in balance. Okay. So as I said, filtering is indiscriminate. If it fits through the opening, it's going to go through. And then the things that we want to keep, we're going to recover in the tubules. So three steps give us urine. First, we filter in the glomerulus. The filtration product, the filtrate, should have no proteins. It should have no cells. It should have no red cells. It should have no white cells. It should have no protein like albumin, for example, or anything else. It should be free of all that. Now we have to reabsorb. We get back 99% of what was in the filtrate. 99% of the water, 99% of the ions, 99% or more of the glucose. We're going to recover all that from the proximal tubule, the distal tubule, the loop of Henle, and the collecting ducts. The collecting ducts are going to recover water and sodium, because if we recover water, the way we do it is we recover the sodium and the water follows. And so as we raise what antidiuretic hormone does for us is simply make the collecting duct permeable to water. Well, does it increase the presence of aquaporins, those passive channels? That's essentially what it does to allow water to come in. So tubular reabsorption gets us 99% of the filtrate, of the stuff in the filtrate back. And then the last step is tubular secretion, to move the substances out of the plasma into the proximal tubule, the distal tubule, the collecting ducts. Stuff that we don't want, stuff that we actually have to, we can't just depend on filtration to get rid of them because they're too big. Proteins that we want to get rid of, chemicals we want to get rid of. So. Filtration is passive. We don't use any ATP to filter. It's all driven by pressure. Now, I guess you could argue at some point, if you really wanted to, that it is driven by ATP because something had to raise the pressure in the blood. But we're just going to say it's passive because the glomerulus doesn't have to use any energy. We force blood under higher pressure into the glomerulus, and since the pressure is all going pushing against the walls of the capillaries, there's no pushback. Everything goes out. 99%. 99% of everything in the blood is going to get filtered. At any given time, 20% of all of our blood is being run through the capillaries of the glomerulus. It does a better job in filter. The reason this area filters and other capillaries don't is because most capillaries aren't penetrated, for one thing, and the pressure is higher here. Capillaries don't like high pressure, but these capillaries can handle relatively higher pressure. So we have a higher pressure in the glomerulus to push the plasma out. There is no backflow because the pressure going out is greater than any pressure trying to push back. And we end up with what we call a net filtration pressure, which is always higher than the pressure in the Bowman's capsule or in any of the tubules. So here's our glomerulus and our Bowman's capsule. The afferent arteriole is over here. You can see it's a larger diameter arteriole. It has greater pressure in here, maybe 60 millimeters of mercury pressure. The pressure inside the glomerulus drops, obviously, because it's going to spread out, but it's still greater than the pressure in Bowman's capsule. So the plasma is pushed out into Bowman's capsule. There is back pressure from the capsule and the filtrate that's already in the tubule, but it's not enough to prevent the flow of blood, prevent the flow of plasma out of the glomerulus. the 80% of blood that didn't get filtered on that particular pass is recovered in the efferent arteriole, but the pressure is much, much lower now. And again, the efferent is a smaller diameter. Afferent's a larger diameter. So we have, we raise the pressure, but we slow the rate of flow through the kidneys. This is pretty important too. Yeah, we have a smaller tube leading out. So we can control we can keep the pressure high in the glomerulus, but it also slows it down because the speed through the kidney is very, very important. We don't want to go through too fast. We don't want to go through too slow. Bad things happen in both cases. We'll talk about this here in a second. So, and then once we get our filtrate into the proximal tubule, we immediately start recovering. See, now we know that the pressure is somewhere between 50 to 60 millimeters of mercury in the glomerulus, but there is a back pressure from the proximal tubule and from Bowman's capsule. So if the pressure in the glomerulus is, let's say it's 55, the back pressure is conveniently around 45. So what happens then is the pressure of the filtrate going into the proximal tubule is about 10 millimeters. We have just enough back pressure from what's already in the tubule. Think of the back pressure like in the pulmonary trunk. When blood in the right ventricle has to open the semilunar valves for the pulmonary trunk, you got to overcome the pressure in the pulmonary trunk. So the ventricle has to squeeze the blood to generate enough pressure to flip the semilunar valve open. Okay, so we're used to this idea of overcoming back pressure. Well, we have back pressure in the filtrate that's already there. We have back pressure in Bowman's capsule, and that leaves a net filtration pressure. And this is an important term. Net filtration pressure is about 10 millimeters. 10 millimeters is just fine. Strong enough to force the filtrate through the nephron, but not too strong that it would damage the structure. And so we see here our net filtration pressure is 10 millimeters. Now this is an important thing to remember. This is where our patients get into trouble. If their filtration pressure gets too high, that's not a good thing, because it means we're shooting filtrate through the tubules too fast, not giving it enough time to get rid of waste products, not giving it enough time to recover what it needs. If it's too slow, stuff that gets filtered the bad waste materials get reabsorbed. We want to keep that filtration pressure around 10. That's a good number. Once if our kidneys start getting out of balance, then we start we start recovering products we don't want to recover. Your kidneys start to fail. So now, another term here is what we call the glomerular filtration rate. This is tied directly to the net filtration pressure. The GFR is proportional to the NFP. There we go. Let's throw some acronyms out there. The glomerular filtration rate is proportional to the pressure. Higher pressure means higher rate. Lower pressure means lower rate. Any kind of change in the glomerulus blood pressure is going to affect the filtration rate. Now, how much filtration rate should we have? We should be filtering about 120 mils per minute. $120 milliliters of filtrate should be coming out from our kidneys in a minute. That is a normal, healthy glomerular filtration rate. And there's, that depends on the filtration pressure, the pushback, the health of the glomerulus, how big are the glomeruli, Are they functional? Are they damaged? Are they healthy? All these things are going to affect. Let's say we're dealing with a perfectly healthy kidney with a perfectly healthy million nephrons with a million glomeruli in the nephrons. And so you're going to have a nice rate of 120 mils per minute. You have a healthy patient with healthy kidneys. We want to keep that nice rate of 120. Because if we get too fast, if our GFR goes up, we don't have time to reabsorb what we want to. We want to recover water. We want to recover glucose. We want to recover salt. Well, if our filtration rate is faster than 120, we're not going to recover all the glucose that's in the plasma. And why is glucose in the plasma? Because it's a tiny molecule and it got pushed through the fenestrations. We want to get it all back. The only way we don't get it all back is if we have so much more, if there's a tremendous amount of glucose in the plasma, we're not going to recover it because it's going to stay there and you're going to see sugar showing up in the urine. We'll talk about that. I mean, we've talked about that with diabetes. One of the signs of diabetes, of course, is glucose concentrations are, glucose is present in the urine. It shouldn't be there. Any glucose we get in our urine normally is all reabsorbed in the into the peritubular capillaries. So if our rate is too fast, we're not going to get it all back. Now, if our rate is too slow, which at first sounds like, hey, that's a good idea. We have a nice slow rate. We got plenty of time to recover everything. Well, it doesn't work that way either. Because if the GFR is slow, if your filtrate's forming and it's going through your proximal tubules slowly, yeah, you're gonna recover all your glucose and you're gonna recover your water and you're gonna recover your sodium and all the things that you filtered out, the things that you want to get rid of, all the nitrogenous waste, metabolic waste are gonna start being reabsorbed. So a slow GFR allows your kidneys to recover those waste products. And that's the whole essence of kidney failure. Your kidneys are failing to get rid of the waste products because your GFR is slow. You are excreting you're filtering out your waste products, but you're recovering them. And those toxins, instead of leaving your body, are accumulating and they're gradually killing your body. A patient that goes into kidney failure will die in about 48 hours after kidney failure starts. That's just sort of a rule of thumb, whatever that means. So, but it's sort of a constant. Once the kidneys start to fail, your patient's going to die in about 2 days, unless you can correct that. As long, and the thing is, we have a really big range here for blood pressure. Systemic blood pressure, 80 to 180. As long as our blood pressure stays in that range, your filtration rate's going to be reasonably okay. Our kidneys are pretty forgiving here as far as it goes. But once we get out of that range, and our patients will do that, then we can either be too slow or too fast. And neither one is good. So, because if we're too fast, we're not going to recover everything we want to recover. And we're not going to probably be able to get rid of the waste products as fast as we want to, the stuff we have to secrete. And if we're too slow, all the things we've gotten rid of are going to come back. So we have to, the GFR, the glomerular filtration rate, is a very important value. How well are your kidneys filtering? And so our bodies actually have 3 ways to control our filtration rate. We don't just leave it to one. And this is the kind of thing that whenever you have blood work, it always shows up on the results of the blood work. They can assess the filtration rate by looking at your blood work. And, you know, because we want to know how healthy our kidneys are. So anyway, the mechanisms we use to control the glomerular, try and say that again, the GFR. We have what's known as renal autoregulation, where the kidneys regulate themselves. We have neural controls involving the sympathetic and parasympathetic nervous system. And we have hormones that regulate this. This is where we bring in renin angiotensin. Remember the other day we talked about renin angiotensin. Renin, when activated, renin will stimulate angiotensinogen to become angiotensin 1, which becomes angiotensin 2. Angiotensin 2 is a vasoconstrictor and will raise blood pressure. And it will also stimulate the formation of aldosterone from the adrenal cortex. And aldosterone tells us to retain sodium, which allows us to retain water, increasing our heart volume, our blood volume, raising our heart rate, raising blood pressure. So, okay, so the intrinsic controls. Intrinsic controls, the kidneys are controlling this themselves. Renal autoregulation maintains a constant GFR for us, which is really, really good. We have two different types of intrinsic controls. This renal autoregulation, we have what are known as myogenic controls, where we deal with changes in pressure in the afferent and arteriole. And we have flow-dependent tubuloglomerular feedback. Flow-dependent tubuloglomerular feedback. And this is where we pick up changes in the juxtaglomerular apparatus. If you remember that thing is located right about the area where the distal tubule butts up against the afferent and efferent arteriole. We'll get to that one in a minute. Myogenic control. Kidney doesn't need any outside influence. Kidney can regulate itself just fine. That's what we call it. Say it's auto-regulated, sort of like the heart being autorhythmic. Heart doesn't need any outside help to beat. Kidney doesn't need any outside help to regulate its GFR, a healthy kidney anyway. If the blood pressure and if the systemic blood pressure goes up from 120, let's say goes up to 130 or 140, the afferent arteriole will constrict automatically, almost reflexively. Because if our pressure goes up, the afferent arteriole protects the kidney by constricting. Sure, the pressure is higher in the systemic circulation, but in the nephron, it hasn't changed. The afferent arteriole constricts, reducing the flow. So the pressure, the pressure of the blood, the elevated blood pressure isn't going to affect our kidneys. And if that's the case, then if we don't allow a rise in blood pressure in the body to affect the kidneys, our net filtration pressure doesn't go up. If the afferent arteriole didn't constrict and your blood pressure shoots up to 140/90, for whatever reason, then that means that the kidneys would be receiving blood under higher pressure and they'd be pushing harder against the glomerulus. You'd have a greater net filtration pressure. We don't want that. We want to keep that net filtration pressure right about 10 millimeters. So we constrict the afferent arteriole, we reduce the size of it, we reduce the amount of blood coming through, and we keep our pressure constant in here. If blood pressure drops for whatever reason, if our blood pressure drops, then the afferent arteriole dilates to increase flow. If the pressure goes up, the afferent arteriole constricts to reduce flow, If the pressure drops, it dilates to increase the flow. So we keep our filtration pressure the same, 10 millimeters of mercury, and we keep our GFR right about 120. So we don't, we don't need any outside influence to tell us how to do this. The kidneys will auto-regulate because they will monitor blood pressure. They're going to pick up on blood pressure. They've got baroreceptors. They measure volume and they know what the pressure is. They can fix that right away. Now, this is not a long-term fix. It's a short-term fix. So we can either dilate the afferent arteriole if the systemic pressure drops, or we can constrict it if the systemic pressure goes up. That's myogenic autoregulation. And so here we see, there's our afferent arteriole coming in, to the glomerulus. There's the efferent going out, and there is our glomerulus. There's our GFR. So if we have a change in the systemic circulation, we can control that right here at the afferent arteriole. We either dilate this to increase the flow, or we constrict it to reduce the flow. So here we have systemic pressure has gone up. So we vasoconstrict the afferent arteriole. The kidney detects the rise in blood pressure and the systemic pressure, and to maintain a constant GFR of 120 and maintain a constant net filtration pressure of 10, it reduces the flow going into the glomerulus. So that 120 millimeters of mercury that's hitting that renal artery, or 140 or 160 or 180, has no impact. We simply reduce the flow going into the glomerulus at that higher pressure, and we still end up with 10 millimeters of mercury net filtration pressure. We still keep 120 mils per minute. And the reverse of that would be, if the pressure drops, then this thing would dilate. We would reduce the resistance here. So, okay, now let's go on. So that's the myogenic control. That's very easy. We simply control the afferent arteriole. Dilate when the pressure is low, constrict when pressure is high. The other mechanism is the tubuloglomerular feedback. I said at that time. Okay. If the GFR is low, it means our filtrate goes through the tubes slow. We don't want that. We don't want to have a slow passage here. We want to keep it at 120 mils per minute. So how do we know? How do the kidneys know that the flow is slower than normal? Well, they do it by monitoring sodium. It's a very elegant little process here. Instead of trying to measure pressure or to measure volume, all we have to do is measure salt. Osmoreceptors, salt level detectors, they measure the salt concentration. All they have to do, if our filtrate is moving very slowly through our nephrons, and we get rid of all the salt by the time we get to the distal tubule, well, that shouldn't have happened. When we get to the distal tubule at the top of the loop of Henle, when we get all the way to the other side of the proximal tubule, the loop of Henle, back up to the distal tubule, we shouldn't be out of salt. When we get to the distal tubule, we should still have a certain amount of salt left in the distal tubule. But if we detect no salt, then the kidneys know that the flow rate's slow, way too slow. So all we have to do is monitor for sodium. And that tells us that the filtration rate is slow. So the tubulo-glomerular feedback is built around being able to detect levels of salt. It's very simple. If the salt levels are high, then we're filtering too fast. If the salt levels are low, we're filtering too slowly. Now, what about the nervous system? And what about the endocrine system? These are what we call the extrinsic controls. Or the intrinsic was myogenic and tubulo-glomerular feedback. The extrinsic controls using the nervous system and the endocrine system. Now these controls will override the kidneys if necessary. So it is the sympathetic nervous system that comes into play. Because remember, the sympathetic nervous system controls the diameter of blood vessels. The sympathetic nervous system can release norepinephrine to cause vasoconstriction or not release norepinephrine to allow vasodilation. If you have healthy kidneys, your blood vessels are dilated. The sympathetic nervous system is not doing anything. If you have if your kidneys are healthy, your blood vessels are reasonably dilated and you're running off of renal autoregulation. Your intrinsic controls are taking care of everything. And that's fine. We adjust the size of the afferent arteriole. We know when to pull out sodium. We know when to pull out water. The filtration rate is about 120 mils per minute, and the filtration pressure is about 10, where everything is supposed to be. That's normal. But what happens if things change? And your patients are going to have all sorts of things change on them. What if your blood volume is dropping? What if you have a patient with low blood volume? Now, I will grant that if your patient is bleeding profusely from an arterial bleed that's spurting everywhere, the last thing you're probably thinking about is, oh, I bet their kidneys have low blood pressure inside there and they're not filtering properly. That's probably not high on your list of things to think about in that type of situation. You know, you might get to it a little later, but right now you're like, oh, look, the blood's spurting. We better stop that and we better replace that missing blood. Okay, but what happens here, if our blood volume drops, our blood pressure drops. A patient that's dehydrated will have low blood volume, for example. So how do we respond to low blood pressure? Low blood pressure will cause low blood volume. All that extra blood's retained in the large veins anyway at that point. So what do? Well, the sympathetic nervous system will kick in and stimulate the release of norepinephrine. We know that norepinephrine is going to cause vasoconstriction. If the adrenal medulla secretes, if the adrenal medulla secretes, there we go. Yeah, there we go. Well, you know, it's about how I've been talking all morning. If the adrenal medulla releases norepinephrine, it's going to cause a systemic vasoconstriction. It isn't just, you know, we're controlling the smooth muscle and the arterioles, you know, at the skin. We're going to have a systemic vasoconstriction if our blood volume has dropped. And if we vasoconstrict all of our vessels, we're going to raise our blood pressure. Now, we don't know if your patient's bleeding out and the volume's low, or if they're dehydrated, you know, or if they've had some sort of systemic shock. All we know is that they have low blood pressure because there's an apparent low volume of fluid. So we vasoconstrict the afferent arterioles. We vasoconstrict all the arterioles in the body. We raise our blood pressure. Constricting the afferent arterioles in particular is going to lower the GFR. Oh boy, that sounds counterintuitive. Because we were just talking about, we don't want the GFR to be too low. But think about it. We have low blood volume. Something's going on. We have low fluid volume. Something's going on here. You know, are they bleeding internally? Are they bleeding out? Are they are they dehydrated? You know, are the extracellular fluid volume is low. So what are we doing? Well, we have to raise our blood pressure. Blood pressure is very low. We raise our blood pressure. We constrict the afferent arterioles. That lowers the filtration rate. If we have less blood being filtered, we keep more in the vessels. Our volume and pressure goes up. So, because what's happening here, when blood volume goes down, the heart's going to start picking up the pace. The heart's going to be, and the heart's going to try and compensate. Our blood volume goes down, and the heart starts beating faster. Your patient that has an arterial bleed spurting out all over the place, the heart doesn't know that. The heart doesn't know that they're losing blood rapidly. All that the heart knows is that pressure is dropping, so I better beat faster. And they beat faster, more blood comes out, and then they have to keep beating faster yet. So your patient bleeds out pretty quickly. Well, when the heart does pick up the pace, the overall blood pressure is going to rise, but there's less fluid there. An easier way is to vasoconstrict everything, raise the overall blood pressure, allowing us to not filter as rapidly and retain fluid. So this is an abnormal situation. The sympathetic nervous system kicks in and gives you a systemic vasoconstriction. Not what we want to see all the time, but it can be done here to bring the blood volume back up. And then if we're dealing with low blood pressure, if we want to raise, if we want to raise our blood pressure, the main way we do it, the simpler approach, than having, you know, and while releasing a norepinephrine from the renal medulla that affects all of our smooth muscle around all of our arterioles is a good approach. This is a better way. The renin-angiotensin-aldosterone approach. The sympathetic nervous system will be triggered. Let me back up here. The key here is to get renin to be released at a structure called the macula densa area. So there's three ways to do this. The cells that release renin are called granular cells. We can stimulate them directly from the sympathetic nervous system. We can stimulate the macula densa cells by detecting low sodium in the filtrate. We can stimulate them to release renin if they don't stretch very much. So we have the nervous system kicks in and says, hey, we need to have some renin. Blood pressure's low, let's release some renin. So it tells the granular cells to release renin. Or a much more elegant approach here is to detect low sodium levels in the distal convoluted tubule. That's what we're going to monitor. It's this distal tubule. The distal tubule is butted up against the afferent and efferent arteriole, and we can detect levels of sodium are low. If levels of sodium are low in the distal tubule, that means that we've had our filtration rate is the kidneys can infer, if the sodium levels are low, that our filtration rate is too slow because we've sucked all the sodium out of the filtrate before it ever got to the distal tubule. The longer the filtrate is running through the tubules, the more stuff gets removed. It also gives waste products more time to come back. So we're pulling, you know, the slower we go, the more sodium we're going to pull out. Conversely, all the waste products we got rid of initially are going to come back in. But right now, we're just looking at sodium. So we're going really slow. We suck out all the sodium. We can detect that. And that's going to turn on these cells called the macula densa to release renin. If our cells that release renin aren't stretched, if there's not enough filtrate in the distal tubule to cause it to stretch, we can release renin. So now let's take a look at this. We have the distal tubule butted up against the afferent and efferent arteriole. That's this area right here. This area right here. There's the distal tubule. There is the afferent arteriole. There is the distal tubule here. And so the juxtaglomerular apparatus is located in this region right here, where this is primarily butted up against the afferent arteriole. Now, the walls of the afferent arteriole have the juxtaglomerular cells, and they contain renin. They have glands inside there that contain renin. And these cells, these granular cells, these juxtaglomerular cells are functioning as a mechanoreceptor. So they can detect stretch, they can detect pressure. Now, this is the macula densa right here. There's the distal tubule cells. This is distal tubule. These are the juxtaglomerular cells surrounding the afferent arteriole and maybe to a little bit the efferent arteriole. Here is the macula densa region right here. The juxtaglomerular cells contain renin. And they're very sensitive to changes in salt levels and in pressure levels in the distal tubule. The mechanoreceptors that are going to be detecting this and the osmoreceptors that are going to detect this in the filtrate in the distal tubule are the macula densa right here. The macula densa cells are chemoreceptors primarily, and they can determine the filtration rate, blood pressure, and blood volume simply by detecting sodium. They don't have to do anything else to find out there's something wrong here. All their job is, the macula densa's job is to constantly monitor sodium. If sodium levels are way up, it means that our filtration rate is too fast. So if sodium levels are high, then it means that our GFR is not 120 mils, it's higher than that, it's higher than normal. If our sodium level is low, it means that our GFR is too slow. Because if we're filtering slowly, we're going to recover all the sodium. If we're filtering slowly, if the GFR is low, it means we have time to recover all the sodium. If we recover all the sodium, by the time we get to the distal tubule, the sodium levels are nothing. And the macula densa detects that. Macula densa says, hey, sodium's 0. We're going too slow. Where sodium's really high, we're going too fast. And that GFR tells us then what the blood pressure is. If our GFR is, if our sodium levels are very high, then our blood pressure is high. If our sodium levels are high, it means that our GFR is fast. And then what makes our GFR fast? High blood pressure. High blood pressure going into the glomerulus pushes the blood through faster. We form filtrate faster. We don't have time to get all the sodium out. So the sodium levels, by the time we get to the macula densa, are elevated. High sodium levels mean high blood pressure. It means a high GFR, and it means high blood pressure. So now we've been able to detect the GFR and blood pressure based on the sodium levels. Blood volume. If our blood volume is low, then we're going to know that our blood pressure is low. So we can detect blood, we've already detected blood pressure indirectly through the GFR. If our sodium levels are high, our filtration rate's high, and our blood pressure is probably high. And that can allow us to determine what our blood volume is. If our blood volume is high, then, if our blood pressure is high, our blood volume is probably low. If our blood pressure is low, our blood volume is probably high. So we can infer all this based on the sodium. We don't have to do any pressure recepting or anything else. We just measure sodium. Sodium is the key. High sodium in the distal tubule means that we weren't getting it out. It means that we're filtering too fast. It means pressure's too high. Low sodium means we're filtering too slowly. We're recovering all the sodium. It means our blood pressure is too low. All we have to do is monitor the sodium. And so the macula densa is picking up on all this. It's measuring the sodium levels. Now, if there's a problem with the sodium, we can tell the juxtaglomerular cells that there's a problem here. Remember, let me go back a couple slides here. Remember, there's the macula densa right there inside the distal tubule. There's the juxtaglomerular cells there. In here is where we're monitoring sodium levels. If there's no sodium present, it means we're going too slow because all the sodium's been sucked out already. If there's too much sodium here, it means we're going too fast because we didn't get it all. So if we have too little sodium in the macula densa, then we can act on this. Two things will happen here. The macula densa will release a hormone that will cause the afferent arteriole to vasodilate and the efferent arteriole to vasoconstrict, meaning that the afferent, if the sodium level is very low, it means we're going through here too slowly. Low sodium means slow. I like that. Low means slow. If we're going through if sodium levels are too low, it means we're going through too slowly. So how do we fix it? The macula densa will secrete a hormone that tells the afferent arteriole to dilate, increasing blood flow. It tells the efferent arteriole to constrict so that we raise pressure by backing up that blood in the glomerulus. That increases our blood pressure, which increases the filtration pressure and the GFR. It also tells the juxtaglomerular cells to release renin. So that in one step, the macula densa causes the afferent arteriole to constrict, to dilate, and the efferent to constrict, raising pressure in the glomerulus because we have a large opening and a small opening, so we have back pressure here. But we also release renin. Renin leads to the formation of angiotensin II. Renin converts angiotensinogen to angiotensin I, which is converted to angiotensin II. Angiotensin II is a systemic vasoconstrictor. We raise our overall blood pressure. And this causes our filtration pressure to come back up and our glomerular filtration rate to come back up to where it's supposed to be. All because we detected too little sodium in the filtrate. That's all we had to do. We had to look and see what the sodium level was in the distal tubule, And if it's too low, it means that our filtration rate is too slow. Low means slow. Our filtration rate is too slow, and we're recovering all the sodium before we ever get to the distal tubule because we've taken too much time. And while that sounds like a good thing, hey, we got all the sodium back. Yeah, but you let everything else come back into our kidneys. You know, everything that we had excreted to get rid of has now come back. So all the waste products have come back into. So now, we didn't even talk about triggering aldosterone to recover sodium and retain water and raise blood volume and blood pressure there. That can also happen too. But the primary thing here, let's detect the levels of sodium in the distal tubule. If it's too low, then our filtration rate is too slow. So we have to raise that filtration pressure. We have to increase the glomerular filtration rate. Now, something else will happen here. What if our blood pressure is too high? We can deal with low blood pressure. What about blood pressure being too high? Here we take into account a high blood pressure. The atria of the heart can fix this. Now, these are all short-term fixes. These are not long-term fixes. A person with hypertension has already blown past or hypotension has already blown past all these short and long-term fixes. But atrial natriuretic peptide, ANP, will cause our blood pressure to drop by eliminating sodium. Sodium seems to be pretty important here. So if we get rid of sodium, we get rid of water because water will follow the sodium. That lowers our blood volume, which lowers our blood pressure. Water always follows salt. Water always follows salt. When we eat salty foods, we get thirsty, right? Everybody, everybody agree with that? We were at Pollo Loco the other night, and their chips don't have salt on them. I said, taste these, see if they're salty. And she said, my wife said, no, they're not salty. I said, well, I stand corrected, but it's the first time I've ever eaten in a Mexican restaurant where they served chips and salsa. Maybe the salsa was salty, I don't know. Maybe they stuck it in there, but they weren't salty. So I have to stand corrected on that one. So anyway, if we control salt here with the macula densa, we're monitoring salt. Salt tells us if our filtration rate is too fast or too slow. Here, we're going to use salt to regulate our blood pressure by regulating our blood volume. If we reduce it, if we get rid of sodium, we'll get rid of water, which will lower our blood volume and lower our blood pressure. That's what we want to do. Because blood pressure is related to blood volume. If blood volume is up, blood pressure is up. If blood volume is down, blood pressure is down. So how do we get rid of sodium? Well, ANP, well, first of all, how's the heart know? The heart knows because the atria stretch. With high blood pressure, we have high blood volume. The atria are being stretched. When the atria are stretched, they release ANP. This is their response to being stretched more than normal. They will tell the kidneys to stop recovering sodium. If we stop recovering sodium, we'll stop recovering water. The water will stay with the salt. The salt's in the filtrate. We're going to get rid of the salt. The water is going to stay with the salt in the filtrate, and we're going to release water and release salt. Because remember, everything that we eat and drink ends up in our blood. So if we have high blood volume, we can lower our blood volume by getting rid of the water. Because it's all in this, it's all in the same loop. Plasma to interstitial fluid, back to plasma, again and again and again. We get rid of the water in the filtrate by getting rid of salt. We lower blood volume, we lower blood pressure. ANP works against angiotensin II. Angiotensin II is a vasoconstrictor, raises blood pressure. We can counteract that by lowering the blood volume. We get rid of the sodium, we get rid of the water. And at the same time, our filtration rate goes up. So we're filtering our kidneys better, we're getting rid of more sodium, we're getting rid of more water at that point. It also counteracts aldosterone, because aldosterone works by sodium retention. Sodium retention, when we retain sodium, we retain water. That raises our blood pressure. But here we're just raising our blood pressure because angiotensin II is a vasoconstrictor. So, okay, last point. We filter every 45 minutes, our entire blood volume every 45 minutes. If we did not recover all of that filtrate, or most of that filtrate, we would be dried up. We would literally dry up. We have to recover 99% of that filtrate. Within an hour, we would be dried up as like a husk, if you will. We have to get back 99% of the water. We have to get back some of the sodium. We have to recover all the glucose out of the plasma. We have to get the amino acids and our vitamins, all the things we want to keep. 99% of what's in that filtrate, we want to get back. We only want to give up about 1.5 liters of water. And so everything's in the kidney tubules. And because we've gone from the glomerulus into Bowman's capsule, into the proximal tubule, and there's where we're going to have to start getting that water back, and the salts back, and the glucose back. And that's where we're going to leave it for Wednesday. So, okay, let me get us out of here. Any questions on anything? Yes.
Anatomy lab, when's the last week?
This week is the last week. We're going to finish up the digestive system in lab this week. So I know we're all thrilled. So, okay, so this is for lab. This last week of lab, we will do the digestive system, then we will be done. So
we'll test on like for this week.
It'll open this week, and I'll leave it open. I'll give you plenty of time to get to it. So it's not like you don't have anything else to worry about. So, okay, anybody else have any questions? Okay, then I'm going to get us out of here.